Good evening, dear students. Today we'll continue inverse Laplace transform. Inverse Laplace transform. I hope you all have done your homeworks. Okay, so on our last discussion we had discussed the partial fraction method of finding the inverse Laplace transform. Today we will be discussing the convolution theorem. Okay, convolution theorem. We will be using the convolution theorem to find the inverse Laplace transform, right? Okay. So we know we have already seen that the Laplace transform of convolution of two functions g tau d tau, we write the convolution like this, is equal to the Laplace the Laplace transform of convolution of two functions is given by the Laplace transform of the individual functions, right? Given by the product of the Laplace transform of the individual functions. So looking at this equation, we can immediately write inverse Laplace transform of fs gs is equal to the convolution of the original functions, right? So this is a very important theorem which we will be using to find the inverse Laplace transform. So you need to understand that if we can express any given function as the product of two Laplace transforms, immediately we can find the inverse Laplace transform of the product of the two functions. Okay, it won't be clear unless you do a problem. So let's look at few examples. Okay, the last day also we had done this problem in a different method. Today I'll be doing this in a different method. Okay, we started with this, right? So we have to find the inverse Laplace of this function 1 by s multiplied by 1 by s minus a. Now this is obviously equal to 1 by s, and now if you match these two equations, this fs is 1 by s and this gs is 1 divided by s minus a. So we have found two functions of s and we know whose Laplace transform these functions are, right? This is the Laplace transform of 1 and this is the Laplace transform of e to the power at, right? So this becomes so easy. We will just apply this formula to find the inverse Laplace of the entire function, right? So this becomes, over here our fs is 1 by s, so our ft is nothing but 1, and over here gs is 1 divided by s minus a, so our small gt is nothing but e to the power at, right? So all you need to do is now perform the integral from 0 to t. We take our ft as this and gt as this, right? So it has to be integration ft minus tau. Over here it is a constant, so it stays as 1, and g tau stays as it is, d tau. This gives you e to the power at minus 1 divided by a. And if you want, you can match the answer with your previous method. This is what we had received even from the previous method, but it is a very helpful one only if you can express the Laplace transform of the given function as product of two known Laplace transforms. You can apply convolution theorem beautifully. Okay. So I'll be doing one more problem for you so that you can understand it properly. Say question is, okay, now example 2. Find the inverse Laplace of 1 divided by a square plus a square, its whole square, right? So obviously you can write it as a product of two functions. So we write it as solution inverse Laplace of 1 divided by a square plus a square, its whole square, is equal to inverse Laplace of 1 divided by a square plus a square and 1 divided by a square plus a square, right? Now these are known forms of Laplace transform, right? It is the Laplace transform of 1 by a sine at, right? Because over here we have a plus and in the numerator we have constant, so we immediately know it is the Laplace transform of sine at, and also this is the Laplace transform of sine at, right? So inverse Laplace of the product of two Laplace transform is the convolution of the original functions. So our original functions are sine at by a sine at by a, right? And once we have been able to do this step, after that it is nothing but a simple integration. So now our integration becomes 1 by a square 0 to t, one is our ft and one is our gt, so sine a in place of t minus tau, because our first function becomes f of t minus tau, so our first function has become sine of a t minus tau, and sine a tau, the second function stays as it is, d tau. So now all you need to do is just perform this integral. It won't take long. Okay, so it is in the form of sine a sine b, 2 sine a sine b, right? So we can write it as 2a squared (0 to t). 2 sine a sine b gives you a cos of a minus b, so cos of a minus b, a 2 tau minus t, cos of a minus b minus cos of a plus b, right? So cos of a plus b, this gives you a at, okay, cos at d tau, right? So now it's a single step, 2a squared sine a to tau minus t divided by its integral on tau, so 2a comes down, 0 to t, and cos at comes out as constant since it's an integral on tau, and you're left with tau 0 to t, right? So 1 by 2a square, tau you put a t, so it becomes sine at plus you put a 0 on t, on tau, so it becomes a minus sine at divided by 2a minus cos at stays constant, so t cos at, right? Okay, so the last I'm writing over here only 1 by 2a cube if you want to give it a proper shape. Okay, these two cancels, a comes out, and it becomes sine at minus a at cos at, right? Answer. So the rest part of the problem is just integration. The first step is very crucial, where you just need to express the product of two Laplace transform as the convolution of the functions, right? So this is the main step over here, where you need to apply your Laplace transform rules, and then it's simple integration. There's nothing much. So this is how you apply convolution theorem to find the inverse Laplace transform. Okay. Now I'll move on to a different point. That is, in the last class I had just touched this topic, but I didn't do any problem. It is the inverse Laplace of derivatives. Inverse Laplace transform of derivatives. derivatives. Like I had mentioned in the last class, inverse Laplace of a function is given by minus 1 by t inverse Laplace of the derivative of the function. Okay. So many a times, like I had already mentioned, many a times we do not, the function whose inverse Laplace has to be found out is unknown form, but maybe its derivative is of a known form. That means the inverse Laplace of the derivative is known, but of the function itself is not known. So at that time we use this formula. This is very helpful. Okay. So just a simple example will solve all problems. Find inverse Laplace of tan inverse 1 by s. We do not know any formula which gives us the inverse Laplace of this trigonometric function, right? But we can very well understand that the derivative of the function of tan inverse 1 by s will give me a known form, because it will come in the form of 1 divided by 1 plus 1 by s square. So that can give me a common form. So let's see what happens. Inverse Laplace of tan inverse 1 by s is equal to, if we apply this formula, minus, it is a function of s, so we have put this and we are using this formula, dds of tan inverse 1 by s. This straight away gives me 1 by t inverse Laplace. Okay, so tan inverse I get 1 divided by 1 plus x square, so 1 by s square, and you have to do this, so it is minus 1 by s square, right? Okay, so these two s gets cancelled, 1 plus s square, and these minus gets cancelled, so I'm left out with 1 by t Laplace inverse 1 divided by 1 plus s square. So now you can see this form is known, right? Because it is an s square plus a square form, so it is nothing but sine 1t. So 1 by t sine t is the answer. So I expect from this example you will understand when to use this formula. This formula will mainly come into help when you're dealing with tan inverse, or you're dealing with logarithms of any function. These can be of help because because the derivatives of those functions have common form, and we know the Laplace, generally we know the Laplace transform forms like those. Okay, so when you have logarithmic functions or trigonometrical inverse functions, this formula can be of help. Okay, so we have completed two main methods of finding the inverse Laplace transform. Now I'll just show you the third way of performing inverse Laplace transform, that is through contour integration. We won't do it in much detail, and also it is not we do not use it as much as we use the other two methods until and unless we are specifically asked to do this method. Okay, so until and unless we are asked specifically to use the contour integration method, we generally don't use, but it's up to you. Okay, so now we'll be seeing the contour integration method. Contour integration of the Laplace inverse integral. So this is the third method that we are going to talk about. Like we have seen, the inverse Laplace is defined by this integral 1 by 2 pi I c minus I infinity c plus I infinity e to the power st fs ds. The form is not that tough to remember, because in the Laplace transform we have e to the power minus st and ft, and it is the inverse, so we have st and the fs. Only this portion you have to be a bit cautious about, that the integration is done on a line. Okay, the integration is done on a line, and the line is extended from minus infinity to plus infinity, right? Sorry. Okay, so let's see the let's see the contour of the integration. So like I have mentioned, this RES, we are in the complex S plane, right? And sorry, this is imaginary S. Okay, and the integral is performed on this line, that is C minus IR, C plus IR. Okay, and what is done is the integral is performed along this line C plus IR, and R is varied from minus infinity to plus infinity. So this is the line along which the integration is done. Okay, so that all the singularities of the integrand comes to the left side, falls on the left side of the line. Okay, that is how this S is being chosen. Okay, so the S is being chosen in such a way that all the singularities of the integrand falls on the left side of the integral. Okay, now to perform this, in general we take a contour like this. Okay, now you all have had a formal course on complex integral, so you know that to apply Cauchy's residue theorem, we need a closed contour, right? So what we do is, to perform this integral over this line, we consider a closed contour like this, and we vary the R term from minus infinity to plus infinity, so that we can apply the Cauchy's residue theorem. Okay, and eventually what happens is, the integral along this curve, that is this path tau, in case of most function, this vanishes as R tends to infinity. So we are left, this integral vanishes as R is increased from minus infinity to plus infinity, and we are left out only with this part. But this contour helps us because we get the closed contour which is required to apply the Cauchy's residue theorem, right? So I hope you all know this and it is nothing new to you. Anyways, okay, so the path of integration is like this in the positive sense, right? And now this is our entire curve, capital C. So from, if we are given any integration like this, what we have to do is, from Cauchy residue theorem, okay, the value of the integral is given by, first we have to go along this path and this path, or along this path, is whatever it is. Anyways, so L e to the power st fs ds plus, it is along this tau e to the power st fs ds. So obviously this is this becomes a closed path, and we have it along the entire curve e to the power st fs ds. And since it is a closed curve which has been traversed in the positive direction, we can immediately apply Cauchy residue theorem, and the theorem is 2 pi I into the sum of residues at the poles, right? Sorry, sum of residue of e to the power st fs at the sorry, poles inside C. Sorry. So we can apply this formula. Now as we vary this R from minus infinity, that is as R tends to infinity, what happens is the integral along this curve totally vanishes. That is the case with most of the functions we will encounter. So we will be left with only this integral along L, right? So we can write, therefore in the limit R tending to infinity, we are only left out with the integral along the straight line which we require, right? C minus IR, C plus IR is equal to, sorry, e to the power st fs ds is equal to sum of the residues of e to the power st fs at the poles of fs, right? Fs inside C. Okay, so you know that I'm not writing. So this is what we are going to apply to find the inverse Laplace transform, right? So let's see an example. I'll just do one example, not much. Like I have already mentioned, we will try not to use this until unless we were specifically asked to use this method. You if you're comfortable with it, you can obviously use it, but generally the other two methods are sufficient to find the inverse Laplace transform in most cases. Okay, anyway, solution. So we need to find the poles. We'll go to the denominator and find whether the denominator becomes a 0. So we know it is s becomes a 0 at I, and since we have a power 2 over here, so it is a pole of order 2, right? So fs has double pole at s equal to plus minus ia, right? Okay, so now all we need to do is just find the residue at these poles. So the formula of residue is known to you, right? This is not a single pole. This is not a pole of order 1. This is a double pole. So you have to apply the formula. I'm just writing the formula over here for if you have forgotten, in case you have forgotten. So had it been a single pole, right, then the function, then the residue would be given by residue of function, say at z0, it would be given by limit z tending to z0, z minus z0, fz. In case of single poles, if this square would not have been there, this formula would be sufficient to find the residue. But since it is not the case, it's a pole of order 2, that is. So in case it is a pole of order k, the general formula is residue is equal to 1 divided by k minus 1, its factorial, limit z tending to z0, dk, dzk, z minus z0 to the power k, fz, where k can go from 1 to 2, whatever it is. Okay. So since our k is 2, we have to use this formula to find the residue at s equal to plus minus ia, right? So let's do it using residue theorem, residue formula. Residue at ia plus ia is equal to limit, like you can see, okay, 1 divided by k minus 1, over here our k is 1, so that term becomes a 1. So now limit, now our s tending to ia, k is 1, so dds of z minus z0 to the power k, that means s minus ia to the power 1, and then we have the function, that is s by s square plus a square h square, right? In the inverse we have a e to the power st term. So over here you have k, right? So we have applied this formula. We have the derivative of the, just a second, this is the formula, just a second. Yes, this is what I was thinking. I have written a bit wrong. It is 1 divided by k minus 1 and d to the power k minus 1 and a k minus 1. Okay. Yeah, because it was becoming a second derivative. Okay. So the derivative is 1 less than the power, right? So over here it becomes this. So now you can do it as Laplace, limit s tending to ia dds, and this s square plus a square, so this can be written as a square plus b square, so a plus b and a minus b, that is s plus ia and s minus ia, right? So this s minus ia square terms gets deducted, so s est divided by s plus ia square, right? So now you need to do the derivative. Limit s tending to ia 1 by s plus ia square. First we keep this untouched and we do the derivative of this term, so it is power st plus s st to the power st, right, minus, now we keep this term as it is and do the derivative of this, so it becomes a minus 2 s plus ia cube, right? So now you just need to replace s by a ia and this becomes e to the power iat 1 plus iat divided by 2ia square minus 2ia e to the power iat divided by 2ia cube. So this 2ia gets cancelled and you have e to the power iat 1 plus iat divided by 2ia square minus this 2ia gets cancelled, so e to the power iat divided by 2ia square, right? So in the denominator I have 2ia square and these two terms cancel out, so we have iat e to the power iat, right? I think it is right. Please do it yourself at your home. So this two ia terms get cancelled, we are left out with one ia, so now it becomes t e to the power iat divided by 4ia, right? Sorry, so this is the residue at ia. Now we need to find the residue at minus ia. I won't be doing that, please do it yourself. So residue at minus ia is equal to, will come out to be minus t to the power minus iat by 4ia, okay? So this is what is going to come out. So now when you have the residue, the inverse Laplace is just the sum of the residues. So therefore inverse Laplace of s square plus a square is equal to t divided by 4ia e to the power iat minus iat. So this is nothing but sine at multiplied by a 2i, right? So this becomes t sine at divided by 2a. So this is your answer. Okay, so I'll be I would like to give you a homework. Please do it by yourself. Find the Laplace transform of s divided by s square plus a square using contour integration, okay? So with this I come to the end of inverse Laplace transform. In case you have any confusion, please do let me know. Okay, and thank you.